So there you go. So let's get started. Topic for today's lecture is network centrality and power. And we'll cover several topics today. So we'll talk about, in general, the notions of the centrality and prestige in the network. And we'll discuss several metrics that you can use to determine centrality of nodes in the network. And after that, we'll talk about ranking on directed graphs. So traditional centrality measures that they are about undirected graphs or undirected relationships, and directed graph, well, it's when you have directed relationships, and we'll talk about subtle differences. So what's the point of centrality measures? Well, the idea is when you have a network, to be able to determine the most important or prominent nodes, or as sociology says, say actors in the network, based on their location within the network. And this is actually a very, very famous graph of marriage alliances among Florentine families in 15th century. And we know from the history that, in fact, it is the Medici family that became the most powerful family, in Florentine back then. And though they were not the richest, but they were sort of strategically married with other families, and they came to power. And so a very interesting paper, 1993, actually investigates the dependency in between the location within this small network and the power they gained because of that location. So at the end of the lecture, we'll look at this network one more time, and we'll try to apply the metrics we're going to learn about today, and to see if there was any explanation why Medici family became so powerful. So we'll consider two types of networks. And one type is undirected graphs, or undirected network. And typically, in this case, we talk about the centrality. So how central the node is to that network. And central means, in general, is involvement in connections with other actors. And those connections can be direct or indirect. And then we'll look at the directed graphs. Now, here, there are, in fact, the terminology here it differs a little bit. Typically, in sociology, when people talk about centrality of the actor in a directed graph, they actually mean that this particular actor plays a role of the source of the ties, or outgoing edges. So in some sense, if that's an actor and there are edges coming from that actor, from him, then we talk about the centrality of this actor. And a little different notion is a notion of actor prestige, when there is an actor or node in the graph, and there are edges coming towards it. And then we're talking about actor's prestige. So when actor is a recipient of many ties or incoming edges. Now, so sociologists are quite picky about differentiating, centrality and prestige. At the same time, you will see a lot in the literature, especially computer science literature or biology literature, etc. You will see a lot that people just talk about centrality and not differentiate the sort of centrality and prestige things. And so we'll stay with the notion of centrality, but we'll definitely emphasize. something with sound, guys. Okay. We'll talk about we'll be talking about mostly using the terminology of centrality, and we'll mentioning I'll mention those points where probably would be more appropriate to say prestige, but again, it depends on the literature that's being used. But one thing that is important to remember that when you have a directed graph, there is a tremendous difference in between situations when somebody is a recipient of the nodes, and in this sense, think about the difference between import or export, or sending emails, receiving emails, etc., etc. So these are different situations. Versus undirected graph, where we just talked about, we're just counting sort of connections for the node. So there is, for this whole thing to make some sense, and for our metrics to be reasonable, there are several graphs for which, just intuitive notion of centrality, some intuitive notion of what we mean by central should be enough to actually find the central nodes. And whatever metrics we come up with, they should sort of do that for us. So if we look at at this what's called star graph, which of the nodes is the most central one, sort of intuitively? Come on, speak up.
A.
Of course, A, right? I mean, it doesn't matter how much, how many metrics I invent and whatever I'm going to try to convince you in, but it's obvious that A should be the most central node, right? What about this graph, the circle?
They're all the same.
They're all the same, yeah. And the idea here that the centrality metric, again, whatever metric I come up with, they should give the same values to all nodes. And if we look at the line graph, well, probably this node in some metric can be more central than these nodes, for example. But these two nodes, say this one and this one, they might be in some sense even equivalent nodes because each of them have only two neighbors, but might also differ because this node D still seems to be like more in the center of the graph. So even by looking at this, it's clear that we could have various metrics of centrality, and the same node can be most central based on one metric and less central based on another. And I just mentioned two of the metrics. One of them would be the number of nearest neighbors, and in this case, in node E and node D, sort of equally central. But if we're talking about, this is a geographic location, like the actual location with respect to other nodes in the graph, well, in this case, node D would be more central. So let's formalize those metrics. So first of all, the first metric we're going to talk about is called degree centrality. So degree centrality is just really the number of nearest neighbors of the node. The metric is just calculated as Ki. Well, Ki is the number of nearest neighbors, and if we deal with, say, adjacency matrix, we just need to sum over rows or columns because the matrix is symmetric and the graph is undirected. Now, sometimes it's going to be hard to do relative comparison of the nodes if we just use absolute value of the node degree, because in some graphs node degrees are very high, in other node degrees can be much smaller if the graph is smaller. So it is convenient to introduce what's called normalized node degree, or another way to put it, it's a node degree that is scaled to be between 0 and 1. So why it is n minus 1 here? Well, the reason for that is because if there are n nodes in the graph, and we select one node and we try to calculate the normalized degree centrality, the largest possible value for the degree centrality for this node will be n minus 1, because it will have n minus 1 neighbors. And so the highest possible, in the configuration of the star, the highest possible centrality for the center of the star will be equal to n minus 1. And star is the most sort of centralized type of a graph where the node reaches the highest possible centrality. And so if we divide by n minus 1 in the formula, we will guarantee that our normalized centrality will always be in between 0 and 1. Okay? Now, sometimes it is not the sort of intuitively geometrically centered node that has the highest degree centrality. And on this little figure, you see that this pink colored nodes, all three of them have equal high degree centrality. So this notion, the notion of degree centrality, is really about a direct contact, right? Number of nearest neighbors. So the most central node has the largest number of nearest neighbors. The second notion of centrality also follows from the simple consideration of paths along the network. And so when we looked, for example, at this line graph, and we said that, well, this node is probably most central node in the graph, we intuitively thought about the distances from this node to all the other nodes in this graph. So distance to this node, distance to this node, distance to this node, distance to this node. And formally, what we this intuition can be converted in the following formula. We can calculate the total distance from this node, from node I, to every node j in the graph, add up those distances, and take 1 over them. And we do 1 over that sum of the distances because we want to make sure that if the node is central, the sum of the distances from this node to all other nodes is the smallest one. And so then the coefficient will be the largest one. And that's why you do 1 over. So the same way as okay, couple things to point out here. First of all, for this formula to make sense, we need to have connected graph. We need to make sure we can calculate distances from every node to any other node. And in practice, it's a good idea to either check if the graph is connected before running the closeness centrality computations, or make sure that the function that computes the closeness centrality in fact does that for you. Because if the graph is disconnected, and if there is a node, say here, there is another piece of the graph, and we try to calculate this distance, well, the distance is infinite, and it really depends on the way your program handles that. So you have to be careful with this. But if the graph is connected and the graph is undirected, and that means you can reach from any node to any other node, then this is a formula. And the same way as we did with centrality, with degree centrality, we want to normalize it. Now, in this case, normalization will really means multiplying by n minus 1. Well, multiplying because this is numerator and denominator. And again, the same story. The most central picture, the most central node in the star graph is this guy, and the shortest possible distance from this central node to any other node will be n-1. And so again, for the star graph, this formula will be equal to 1. So centrality index is in between 0 and 1 and reaches 1 for the most central node in the most central type of graph, which is a star graph. So if we look at this example, this is the most central node, the node that has the highest closeness centrality is this blue node. It's right here. And you know, why is it so? Well, you can think about it the following way. If we just start calculating those distances here from the central node, okay, we have this one step distance to that node. To each of those nodes, there are 2 steps to reach, and you do it for all of them. But if we take, say, this guy, then it will have several short distances, but for a lot of nodes, it will have to go pretty far. And so the total sum of all the distances will be pretty large. And if you calculate those distances and compare them, then you will realize that it is the central node that does have, so this node will be the most central in terms of closeness centrality. So again, whenever we talk about sort of intuitive centrality positioning within the graph, sort of geometric center of the graph, if you wish, it's the nodes with highest closeness centrality that are closer to sort of geometric center of the graph. Now, that's sort of the 2, you know, fundamental basic ideas for the centrality. But there are also different ways to think about centrality. Let's look at this graph. Which nodes in this graph have the highest degree centrality? Well, you know, just by looking at this, it's easy to see that, say, you know, this node has 1, 2, 3, 4, 5 nodes connection, and this node also has a pretty high degree centrality. If we start talking about closeness centrality, well, you need to actually calculate things, but I believe that it's going to be this node that does have highest closeness centrality if you add up things. But at the same time, it's obvious that the node A has a prominent position in this graph. So it is, you know, of a lot of importance. And the reason for that is because it really acts as a bridge between between 2 groups of nodes. And so we should be able to somehow also, you know, put some number on that. That characterizes this, you know, bridginess of the node, the fact that it actually connects these 2 separate communities. And there is a centrality metric that actually takes care of it, and it's called Betweenness centrality. And it's defined the following way. It is calculated as a number of shortest path that going through the particular node. And so if we start computing shortest paths from every node in this graph to every other node in the graph, well, there'll be some shortest path that, say, for example, goes from this node to this node, and it goes this way, right? Or from this node to this node, this is the shortest path. But at the same time, for every node, if we want to compute the shortest path for any node from this red nodes to any of the blue nodes, this shortest path will have to go through node A. So however we want to do this, it will go through node A. And because of that, node A will be always on the center of all the shortest paths. So you can think about, maybe communications between people. This is a person who knows both groups of people, and so it has this advantage to be a connector, and so all the information should go through this node. And when we think about information, we think about sort of flow along the shortest path. So from the formula point of view, what this says is the following. If we calculate the betweenness centrality for a particular node, let's say I will draw this picture. Say we want to calculate the centrality between the centrality for this node. What we need to do is we need to calculate the total number of all shortest path from all the nodes that go through this one. And so let me add another node here. And so to do that, what we do is the following. We take this node and we calculate the shortest path from this node to say this guy, which is 1, distance 1. We calculate the shortest path that goes from this node to this node, that distance 3, and etc. So that is this number, the total number of shortest path. Now, there is also, we also normalize it to the total number of shortest path between two nodes. Well, the point is the following. If you have two nodes in the graph, say node A and node B, it is very possible that there is, for example, this type of structure in the graph. And so in this case, there are two shortest paths of equal length between nodes A and B. So there is this shortest path and there is this shortest path. And if we want to calculate, for example, the betweenness centrality for the node I here, we need to, well, the centrality will be not 1, but the centrality will be 1/2, because though there is a shortest path from A to B going through I, there are actually two alternative paths. So you can go that way or that way. And so the role, the value of the node I will be 1/2. And so there is this one path that goes through I, and there are two passes between, well, it's actually node S and node T. Okay? Now, what that means is that, again, between the centrality to calculate it, we need to make sure a graph is connected. And also, it's pretty intense computation because we try to compute shortest path between all the pairs of nodes. And the same way as before, we also can talk about normalizing it. And in this case, normalization factor is given by this number. Well, what this number is actually just how many ways you can connect n-1 nodes with n-2 nodes. So if you have one node and we fix it, let's say this node, the total number of shortest path in between the leftover nodes will be n-1 times n-2. Okay. And the factor 2 comes here from the fact that we do not want to double count since the graph is undirected. But the key thing to remember here is that the node with the highest betweenness centrality is the node that is positioned on many shortest path between other nodes. So on the graph structure, it is this connector node. Okay, so these are sort of three major fundamental metrics of centrality, right? Any questions about that? No questions. All right. So if I ask you right now to come up with, say, another metric of centrality, sort of your metric of centrality, what else did we take into account? Sort of any ideas? What else can we do?
of a number of nodes.
Number of nodes, you mean directly connected to a node?
No, I mean the total number of possible components in the nodes that are in the graph.
Okay, you know, that's possible. That's a possibility. There is something, okay, so we actually did somewhat, you know, somewhat mechanical calculations in the sense we looked at the structure of the graph and said, okay, well, you know, the centrality is either sort of very, very much local, which means it depends on a direct connection to the node, or we're looking at all kind of pathways that goes through the particular node. One other idea that you know, shows to be very fruitful is the following. The idea is the following. For a node to determine, to sort of connect the centrality or the importance of the node to the importance of its neighbors. And so think about this. You might have lots of friends on the Facebook or you know, any social network. And how do we measure your importance? Well, you know, we had 3 metrics. You know, how many friends you have. Yes, it does tell us something about you. And how sort of strategically you're positioned within the graph in terms of, you know, how easy for you to reach all the people in the graph, which is a closeness centrality, and how much you're on sort of, you know, on a pathway to all the connections between different peoples, which is betweenness centrality. What we're missing in those 3 metrics is the fact that, you know, that if you're connected to important people, you're probably more important to that, you know, society than if you're connected to unimportant people. So in some sense, you know, if among, you can have, you know, thousands of friends, of fellow students, but, you know, if among your friends, let's say you have a president among your friends, well, you're probably more important than so the president will give you more weight than, you know, hundreds of other students. And so idea is in this sort of recursive definition that importance of the node in the graph, VI, let's say, will be proportional or will be calculated as a sum of the importance of its direct connections. Now you can say, okay, well, great, but what about the importance of these direct connections? Because we need to know that their importance to calculate the importance of this node. Well, their importance is proportional to the importance of their neighbors. And so importance of this node will be proportional to the importance of this node and also that node. And importance of this node will depend on the importance of this node and that node, and et cetera, et cetera, et cetera. So it's like chasing you know, your own tail, right? In fact, under certain conditions, you can actually calculate that. So formally what it says is that the importance of node I is equal to just the sum of the importance of the nearest neighbors. Now, you do not want to actually do just the sum, because what's going to be happening if you try to sort of iterate this process, and iterate, I mean, we start with some values of this V, we calculate, we update and calculate the summation, and then we take this and plug it back there and calculate it again, and calculate it again, and calculate it again. And so if we just start adding up things, the numbers will just grow. And so we need some sort of balancing here. We need to control this addition. And to do that, we need to introduce some sort of normalizing factor on every step. And if you do that, it's very clear from the mathematics that what we have is we have this equation. Now, how many of you know what this equation means? So what is it called? So have you seen AX equal lambda X?
Yes, I have.
I'm sorry, say it again?
Yes, some of us have seen this eigenvalue equation.
Right, this is an equation for eigenvectors and eigenvalues. And so lambda is an eigenvalue, X is an eigenvector, right? So it's traditional, sort of the standard eigenvalue eigenvector equation. And so what happens is, as a result, if you solve this equation, you get a bunch of eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4, if you remember linear algebra a little bit. And you have eigenvectors, or vectors that corresponds to those eigenvalues. And so the idea of this eigenvector centrality is the following. We choose the eigenvalue that is eigenvalue number 1, which is the largest one. And we'll take eigenvector that corresponds to this eigenvalue. So, we have a matrix, we solve this equation, and we get eigenvectors, and this is eigenvector number 1. And it has some numbers, so the components of this eigenvector, I'll just make them up. And so those numbers will act as the centrality metrics for the nodes in the graph. So this will be our centrality metrics. And on this picture, I'm showing you a little social network with the size of the nodes proportional to their eigenvector centrality. And that's sort of the key feature, the key differentiator here will be the following. It's a node, the node will have high eigenvector centrality if it is connected to nodes with high centrality. So in fact, we'll see this theme, recurrent theme, through the rest of the lecture. But it's very, very important. So the node has high eigenvector centrality if its neighbors has high centrality. Person is important if the person is connected to important people. All right. And so when you look at the graph that has nodes with high centrality, you will see that they usually sort of group together. They reinforce themselves. Okay, makes sense? Okay. Well, the good news is, as pretty much with every other thing in iGraph, you really do not need to take and solve take a matrix and write down the equations and solve them. iGraph will do it for you by just simple command, eigenvector centrality. So here are a few examples, just hopefully will help you a little bit to realize the differences. This is a very particular network just designed to show you the differences in between metrics. So closeness centrality, as we discussed, as we talked about it, is a centrality that highlights nodes that are central to the groups, which means the total sum of the distances from those nodes to every other node in the graph is small. And it will be nodes that are sort of centers of clusters that will have high closeness centrality. By looking at this network, what nodes do you think, which nodes will have high betweenness centrality?
The ones in the back, that connect the components.
Mm-hmm. So, I mean, it sort of seems like these guys might, right? They're sort of bridges. And, if we look at the next slide, well, indeed they are, right? So these are the sort of the bridges. These are the nodes that have high betweenness centrality. So like they lie on the pathways from a lot of nodes to a lot of other nodes. And the last comparison here is eigenvector centrality. So it's hard by just looking at the picture to guess which group of nodes will have a high eigenvector centrality. But what's clear that those nodes will typically be next to each other. And so here are the group of nodes with high eigenvector centrality, right? So they're central, but they all live within the same cluster. And so what's done is we compute the centrality metric using iGraph function, and we'll select nodes that has the top 6 nodes here, 7 nodes that have highest centrality metric, and they are highlighted here. And final comparison is this picture. In fact, it's taken from, I took it from Wikipedia. The idea is the following. So you have a geometric graph, and which means it's a graph that is embedded on two-dimensional surface. It's sort of like a grid, but sort of distorted grid. And we look at different centrality metrics here. And again, the first one here is a degree centrality, and and the color-coded proportional to the value of the centrality. And so, it picks up some nodes here and here that has lots and lots of local connections, and they have high degree centrality. Now, B gives us closeness centrality, and this is this diagram. And with closeness centrality, it's obvious that the nodes that are sort of, the closeness centrality gives us sort of geometric centrality of the graph. And so it's a node that, in geometric center of the graph that will have high closeness centrality. And nodes here on this periphery, they will have pretty low closeness centrality. Now, between the centrality are those bridges, and here they are. It's not very obvious right away, which has the highest. So this is the highest bridge, and this is the highest. And finally, eigenvector centrality is also not obvious just by looking at the picture. But what we, again, what we should be able to tell right away is that, when we deal with eigenvector centrality, it will be a group of connected nodes that all of them will have high eigenvector centrality, because it's sort of reinforcing notion. Okay, so any questions about the centralities? No questions. All right. Actually, I'm seeing that it's pretty dark in the room. You guys falling asleep there, or maybe we should turn light on or open windows, or I don't know. We still have some time to go, so
everything is all right. They say it's okay.
Okay, well, I can barely see that. It looks like it's very dark in Moscow. Huh? Okay. So we talked about the centrality, and the centrality is a per node metric. So which means, for every node in the graph, we calculate that. But there is also a notion that, there are different graphs, they look different. Like, for example, if we take, say, this graph, or as we saw, say, this graph, by their structure is very different from the star graph, or graph that has sort of stars here, but maybe another star here, etc. So, and the difference, sort of, again, intuitively, the difference is the following. In these two graphs, all the nodes pretty much play the same role, right? They're very similar in terms of number of neighbors, and similar in terms of the roles and locations in the graph. And so if you measure the centrality values for nodes in this graph, they will be very, very similar. So the nodes will have very similar centrality, whatever centrality we take. And the same true for circle, for this circle graph, we talked about it, those nodes are all equivalent in terms of structure, and so the centrality for all of them has to be the same. Versus graphs like this too, where there is one node that very distinct in terms of centrality, very important compared to other nodes. Or here, there are several nodes that would be very important compared to other nodes. And so what one can do is one can compare the roles within the graph and see how different they are, how different those metrics for the nodes within the graph. And that will be the characterization of the graph. So if graph has a structure that emphasizes certain nodes over other nodes, we talk about centralization of the graph. And we're saying, okay, this graph, the graph that does have the structure where some nodes are more central than others, have high centralization. And those graphs where nodes pretty much all similar in terms of their roles and positions, they have low centralization. And so centralization as a measure or a metric, it's a network metric, so it's computed for the entire graph. And it's defined usually the following way. It is how central the most central node with respect to the other nodes. And so pure technically, it's computed as a difference of centralities for every node, normalized by the most central structure you can possibly have. And the most central structure is always a star. So you take a graph and you calculate numerator, and denominator comes from building the star of the same number of nodes and just computing this value for the star. And again, you don't really have to do anything yourself. You just call those functions within iGraph. You pass a graph to those functions. The functions will give you back the value. And what you need to remember that for this type of graphs, the value for centralization will be pretty high. For this, it will be relatively low. And so it's a metric that tells you, how different nodes centrality measures are for the nodes in the graph. All right. So again, just in general, centrality is per node. Centralization is an entire graph metric. If you have n nodes, you'll have n centralities, but one centralization measure because it's a graph measure. All right. Any questions there? Okay, moving on. So now life getting a little more complicated and interesting when we're getting into the directed graphs. And in this case, we need to distinguish between sort of choices made by the node or choices made by an actor and choices received. Well, I mean, in some sense, it is, I'm sending out emails, so it's the choices that I made. Right. So my emails that I'm sending out will be outgoing edges from the node. Let's say we take the node number 2, and there are some outgoing edges here. Now the choices I haven't made, but that are sort of received. The choices received. It's the edges that coming towards me from other nodes. And in this case, say, this node, and there is this node. So if we like incoming emails, if you try to model economic networks, there is expert and import, right? If you model citation networks, which papers cite which papers, it's also a huge difference, right? I'm citing someone or somebody is citing my work. So there is a difference in incoming and outgoing edges. All right. Now there are some situations, like friendship network, it might not make any difference because okay, we're two friends. But by the way, Facebook, for example, does store information on who sent whom friend request. And that graph will already be directed. So who initiated the sort of friendship. So within the directed relationships, you can actually do two things. I'm missing a slide here. Okay, with directed relationships, you can do two things. You can talk about what's called the centrality, as we talked about it before, and also you can talk about this sort of notion of prestige. So centrality is usually associated with outgoing edges, and prestige is usually incoming. And the idea is, again, very simple, that, okay, the notion of prestige, somebody is prestigious if a lot of people, points to the person, right? And that's sort of prestigious, that's where this comes from. And actually prestigious if others believe that he's prestigious. It's not his action, it's actions not directed toward him. So if talking about centrality, we can pretty easily extend the ideas of the centrality that we did for undirected graph to the directed case. So if we do degree centrality, again, typically it is about the degree of outgoing edges, outgoing links. So what you do is you differentiate the outgoing and incoming edges. So this node has overall degree of this node degree is 1, 2, 3, 4, 5, 6, 7, 8, right? Degree for outgoing here is 1, 2, 3, 4, 5, and degree for incoming is 3. Okay, so you can have 3 metrics for this node in terms of nearest neighbors, right? Overall, there are 8 nearest connections, but outgoing edges 5 and incoming 3. And typically, when you calculate degree centrality for the directed node, it's calculated for outgoing edges. Now, closeness centrality, you have to be more careful here. And the reason is, again, when you have a directed node and directed graph, it's important for us that this is how this particular node, how you can start from this node and reach other nodes. And so in this case, for example, if you have node here, an edge comes towards this node, and we want to calculate the closeness centrality for this node. We have to follow the direction of the edges. We cannot go against the edges, against the direction of the edges. And so this metric in this case is very important to remember, that dij really means distance from node I to node j. So this is node I, these are node j's. And in this case, in the case I have shown, for example, distance from this node to this node is 1, right? It's 1 step. Distance from this node to this node is 2, because there are 2 steps. But distance from this node to this node will really be infinity. It's not reachable, because the direction of the edge is towards node I, and we need to calculate distances from node I. So that really means that when you calculate that closeness centrality metric in the graph, the programmer that does it has to be very sort of particular and precise in terms of how to deal with this, distances to the nodes that are not reachable because of the direction of the edges. And you have to somehow, take care of it. And one way to do this is to just sort of ignore the nodes you cannot reach and don't include them in the closeness centrality. So, degree centrality in this sense is very easy and makes total sense in directed graph. Closeness centrality, used a little less. Betweenness centrality used even less in directed graphs simply because here, when you calculate all the shortest paths, you need to take into account, again, all the directions. So it's not just the shortest path, it's the shortest path that follows the right, the direction of the arrows that exists. And it's not very obvious sort of, how to interpret, in many cases, this betweenness metric. But it can be computed. Another thing that people quite often do with directed graph, they take the directed graph and they say, okay, well, let's just analyze the structure. Forget for a minute about the directions on the sort of the direction of the graph. Just preserve edges, okay, and make sure that that every time you have it in a direction, you just drop the arrow. Here's the edges. Let's calculate the metrics. Yeah, it's one of the ways to analyze the structure, but it's really not very sort of appropriate here. At the same time, when we deal with directed graph, there are several set of metrics that works really, really well. So again, as I said, on this picture, the degree centrality works really well, and we'll talk about a couple more metrics. And one of them is this idea of status or rank prestige. And it is very, very similar to eigenvalue centrality. But now we're dealing with directed graph. And so the idea is sort of very similar. So the idea is the following. So let's say we want to calculate the prestige of the node number 11. Well, the prestige of the node number 11 is computed based on the prestiges of node number 5 and node number 9. Okay? Prestige of node number 8 is computed from prestiges of node number 3 and number 7. And number 7 in turn, the prestige of number 7 depends on prestige of number 11. So here, prestige follows the directed graph. Okay, so the person is prestigious if other prestigious people points to him and tell him that he's prestigious. And again, the sort of the circular connection, and pure numerically, what it says is a prestige of a particular node is equal to the sum of the prestiges of its neighbors, and it can be written as their linear combination here. And if we use matrix notation, it's really just a matrix multiplication. Okay, and the same way as with eigenvalue and eigenvector computations, the way to do this is to assign initial values of prestige to every node in the graph, and then iterate. So we set up initial values of prestige. Let's say we will give initial values of prestige equal to 1 to every node in the graph, and then we take this and put this into the formula and start iterating, updating, and hopefully at some moment the values of prestige for every node will stop changing. We'll stop changing through the iterations, and then we'll say, okay, well, iterations converged, and here are our prestige values. I mean, that's a beautiful idea. It sometimes works, sometimes doesn't. In fact, if we try to find what's called the stable point, again, we'll get, the idea here is that the stable point will happen when pt plus 1 is really equal to pt, and sort of equal to some value p, so it stopped changing, and so that means that p is an eigenvector that corresponds to eigenvalue equal to 1 for that equation. And we know that, well, first of all, this solution, might not exist, and non-trivial solution only exists when the determinant of this matrix is equal to 0. And I'm not going to go into the details of the mathematics here. You can correct it as we did previously, but there are other difficulties. And just to understand the difficulties is, first of all, there is a cycles. And let's say, we try to calculate the prestige of node 7. Well, it depends on the prestige of node 11, which depends on the prestige of node 9, which prestige depends on node 8, which in turn depends on the prestige of node 7. And when you have the circular dependencies, things might not converge. So you might have the sort of oscillations of prestiges. And there are other things. Let's say, if we take here node number 5, nobody points to this node. And that means there is no other node that can sort of reinforce node number 5 prestige. And which means, if we keep iterating in this picture, the prestige will leak out from node number 5, and it will at the end will have 0 prestige. So we need sort of prestige to keep coming for the system to work. And there are more sort of technical details. Again, if you're interested, you can look in the papers. But in general, this nice approach will have lots of troubles. And in fact, when sociologists in 1953 proposed this method, they ran it for small graphs, and they came up with a lot of interesting little ways to try to fix problems. Unfortunately, those fixes were not very much universal. Surprisingly, the solution to this problem, and the whole bunch of new ranking methods on graph, came from web search. And in fact, it came from Google, and it was called PageRank, and supposedly it's it's a formula that made sort of Google. So the idea is actually very simple. When you have two pages on the web, they're connected by hyperlinks, right? This HTTP, etc. And you can follow those hyperlinks when you go from one page to another. And so in some sense, web graph is really the social network or graph of endorsements. So somebody, it's endorsements by people who create those pages. If someone puts a link from his page to some other person's page, it really means that he endorses that page. So in reality, so if A is putting a link to page B, right? So it means it endorses page B. It also means in the language of this prestige, it really means that the prestige of a site or page B is getting higher because there are a couple pages, say A and C, pointing to page B. And so you can actually calculate all the metrics we talked about, and you can calculate the sort of the rank prestige for this thing. But we'll have all the problems we saw previously. Now, there is a way to transform this problem into something easily solvable. And the idea is that's what PageRank guys came up with. So they said the following. Let's look at this, and they propose what's called random surfer model. So the idea is the following. So we try to model the behavior of a person on the web. And again, this is year 1998, right? The web just became popular for search engines, and so typical behavior would be the following: somebody goes to some web page, looks around, and if the person wants to discover the rest of the web or more information, he follows the links from that page. And he gets onto the new page, let's say, on the page C, follows the links, get on the page B, stays a little bit and then follows the links from page B to another page. And if you have a bunch of links on the page, you might select sort of randomly one of them. But let's say you're on the page A and there are either no outgoing links from that page or you don't see anything that's relevant to you. What do? Well, you can sort of randomly jump to any other page just by typing in the URL. Now, this is a very simplified model of user behavior, but it gives you an idea of how to model the process. And in fact, what I put here is the direct citation from their paper, from paper by Brin and Page, the founders of Google. So the idea is the following: the person that sort of in this random fashion browses the graph, going from one page to another, and eventually he spends more time on some pages than other pages, and he spends more time there because he visits them more often. And so the probability to visit a particular page is called this PageRank. Just probably putting it a little different way, imagine that you're in a city, and it's a city with one-way streets, and the city has well, there are intersections and there are squares, and you can just come to any intersection, you can take any turn you want and follow another road, right? So this is a city map. And let's say you're driving, so you need to follow the signs, the directions on the road. And so you just keep walking or driving around the city. And every time you get on a new square or intersection, you take a random turn. And if this process goes for a very, very long time, you will be coming to the same sort of corners and the same squares in the city more than once. And again, think about some European cities, probably older cities with squares and a lot of streets coming into it. And eventually, if you start counting how many times you've been on the particular square, you realize that you actually appearing on particular squares, on some squares more than on others. And that frequency really means the probability that the random walk that you're doing will have higher probability for you to be on that square than on another. And then what you can do is you can rank all the squares in the city based on that probability. And that probability is what's sort of called PageRank. So the probability that the random surfer will come to the page. Now, if we sort of formulate the problem in this fashion, there is a very, very good mathematical theory. It's called random. It's Markov processes. It's a random walk on a graph. Very well developed theory that gives us a lot of guarantees about solutions, and it's all solvable. So what do we need to do to make this work? Well, there is really there are actually two changes we need to make to that original prestige formula we looked at a few slides ago. So what we need to do is instead of writing as we did previously that pt plus 1, I'll just remind you, is equal, say on I, equal summation on the nearest neighbors, and we did this with the matrix calculation. So instead of just adding up the values that comes from the nearest neighbors, we will need to normalize them. So normalize them by their out degrees. So the idea is the following. When you are, say, on the node 2, you can actually follow either this edge or that edge. And so that means that the probability to go either to the right or to go to the left is equal 1/2. It's not 1 anymore. Or if you on the node 4, you have 3 ways to go. So the probability to follow one of those edges is 1/3 because there are 3 ways to go. And so in this fashion, we can actually write what's called transition matrix. And the transition matrix is the adjacency matrix where you normalize it by out degrees. And that makes it a transition matrix of probability of transition from nodes to nodes. That's sort of one change that we need to make. And another change is this idea of teleportation, which means when you're on a particular node, you can either follow the edges from that node on the traditional random walk fashion, or randomly jump to any other node in the graph, even to those nodes that are not connected to this node directly by edges. This is modeling when person cannot follow the link and just sort of jumps to types in random URL and move on. Or again, like if you're these days browsing Facebook, you go to your friends, then you follow their friends, but then you're getting tired and you just I don't know, finding some random person to look at the profile. So putting this whole thing together, we'll get a little bit different equation. We'll get an equation for the probability to be on a node at the time moment t+1. It actually now has the formula has two components. One is the probability to get on that node from the nearest neighbors by the sort of random walk step. And the second one is the probability to land there based on the sort of teleportation. And what you need to do in this sort of formula, you need to balance those two probabilities, balance two options. And this is a parameter alpha that you will see in many PageRank computations. This parameter really tells you how much more you prefer to follow the structure of the graph versus sort of random jumps. And if, say, in this formula, I take alpha equals 0, then this term, which is a walk on the nearest neighbors, will be 0, and we only have long-range jumps. If, on the other hand, I put alpha equal to 1, this term goes away, and we'll just have regular random walk. In order for computations to converge, it's good to have alpha, greater than 0 and less than 1. And traditionally, alpha is selected, and at least that was done for the PageRank computations for the web graph, is selected to be 0.85 as a parameter. But this is the parameter that you can tune. And then you select this parameter again. This parameter balances out sort of the random walk portion of the algorithm, which is just following the edges, and the sort of the far-reaching jumps in between unconnected nodes. And to solve this, you need to solve this eigenvalue equation. And again, with iGraph, you don't worry about it. You just call the PageRank function. Here's the example. This is a PageRank computed for some graph. There are a few things I want to point out. PageRank is close or somewhat similar to the in degree of the nodes. So the nodes that have, we talked about it, that the PageRank of the node will, depend on the PageRank of the neighboring nodes. But in fact, if there is a node with lots and lots and lots of incoming edges, most likely will have pretty high PageRank. So in many cases, PageRank will be proportional to in degree of the node. So the higher the in degree, the higher will be PageRank. But it's not always, it's not always the same. I mean, if it was always the same, there would be no reason to have this PageRank thing. here is an example for you. Notice now on this picture, the nodes are scaled according to the PageRank values. Now look at these two nodes. They both have two incoming links, but their page ranks are different. According to the PageRank computation, this node is more important than this one, has higher page rank. And the reason why, well, because if you look at this picture, it seems like the nodes that points to that node will have higher page ranks than the nodes pointing to this node. And you can also see sort of situations, let me see, okay, here, where there's a lot of connections for this node, but it's sort of less important than that guy. So again, the in degree for the node can be approximation to a page rank, but it is not exactly page rank. And the idea of the page rank, again, it comes to this random surfer model. In fact, this calculations, the PageRank calculations became so popular that these are sort of page ranks of the world. So people did lots and lots of ranking based this algorithm. For example, there's a tweet or Twitter ranks. These are you take a Twitter graph and you rank tweets based on this graph. Social page rank, this is, let's say, you can take the Facebook and social network and calculate which person is more important based, or rank all the people based on their connectivity patterns. Bookmark rank, here is your bookmarks. The story rank, here is stories, chemical, road rank. I mean, cite rank, this is you take a citation graph, which is a directed graph, and again try to find out which person has the highest rank, or sort people by rank. Investor rank, this is again investments and how much money by different people invest in different things, and so etc. 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 Oh, sports rank, this you can actually create a graph of teams playing against each other, and you can calculate put the direction when one team is winning over another team, and also calculate the rank. So PageRank became the sort of workhorse of ranking on the directed graphs, and compare to other metrics we talked about for directed graphs. It's very, very stable and very scalable. So you can actually take literally any graph you want, put it in a computations, and you'll get the sort of the page rank of it. All right. So any questions about this? So when we speak about directed graphs, I want you to remember first the in degree. So this is the degree for the nodes as a degree metric, and second is of course page rank. Now there is one more idea that I would like to discuss. This idea also came from the web, and in fact, the algorithm is called Hubs and Authorities, or HITS algorithm. And the idea is the following. I think it's a very beautiful idea by John Kleinberg. The idea is the following. Let's say we look at the citation, at the scientific citations, right? And if you read scientific literature, you realize that there are usually two types of papers in the scientific literature. One type of papers is sort of original research papers, right? When the person writes an original research paper, he has some authority about this research subject, and he made some experiments, right? And as an author of the research paper, when you write research papers, what you usually do is you usually, at the end of the paper, you put citations. And citations can go to, well, first of all, it can go to other research papers, So you can, cite other research papers. But quite often, you also cite a very different type of papers. In every research community, once in a while, somebody gets and writes their review, right? Review of the state of the research. And so quite often, when you write your research paper, you do cite reviews papers, sort of large reviews. At the same time, if somebody writes a review, well, he cites always, original research. And so that's where Kleinberg got the idea. So he said, okay, well, it's clear that every paper has this sort of two sides of it. One side of the paper is that it actually acts as the original paper, and so it has some authority to it. And the other side of the paper, it actually acts a little bit of a review paper, and in this sense, he said, he called it hub, as a sort of hub, as a connector. And so what you can do is you can create the sort of logic that if you have a good research paper, it's such paper that cites very good reviews, and good reviews will always point to good research papers. So, speaking in terms of the language Kleinberg proposed, he called the research papers authorities, right? And the review papers, these are hubs. So this is research and review. And what he's saying is that reviews, they point to good research papers, right? And good research papers, they're cited by good reviews. And so one can actually introduce the two metrics for every node. The metric of sort of authoritativeness of the paper, sort of authority, and the metric, the measure of, well, he called it hub or hubness, or sort of how the level of reviewing quality. And so what he said is that good authorities are those authorities that are referred by good hubs. So good reviews pointing to good research papers, and sort of the other way around. Good hubs point to good authorities. Again, this is very much a recursive definition. This AI depends on HJ. So authoritativeness of a paper depends on the hubness of the neighbors, and hubness depends on the authoritativeness. But you can take those two equations and, in the fashion we did before, solve them together. And I can rewrite this as a linear algebra in matrix format, and then it will again become an eigenvalue and eigenvector problem. But in this case, it's an eigenvalue and eigenvector problem, not for the matrix, not for adjacency matrix itself, but for the combinations for the scalar product of two adjacency matrix. Either adjacency matrix times transpose, or transpose matrix times adjacency matrix. And that allows us to calculate two vectors, A and H. And these are two vectors, A and H. And so, which means every node will have two values corresponding to it. The authoritativeness of that node, which means if it's a good review, it's a good original research, and hubness, which means it's a good sort of review. So you can think about this hubness as a node is a hub if it is connecting a lot of other nodes. Think about airport hubs. The airport, there will be a hub. It's an airport that has lots of flights going in many directions, right? So here's an example. It's the same directed graph. This directed graph is for some blogs, political blogs, and I calculated here the hub score and authority score, and scaled nodes according to those scores. And you can see that high hub scores is typically these nodes that are sitting in the center and well connected to sort of authorities. And authorities are those nodes that here that sits on the fringes. Well, and there, of course, there are authorities here in the center because a bunch of hubs connected to them. And there is a different scale here. These nodes seems to be more authoritative than others based on the fact that they're pointed to by, say, this node that has very high hub value. And these guys in the center that do not have any sort of hub value, but they have very high authority value because there are a bunch of hubs here pointing to that. So this is actually a very, very interesting approach that allows you to differentiate the roles of the different nodes in the graph, and think about some nodes as aggregators of information and other nodes as sort of created of that information. And among those creators, there is authority score, how authoritative they are, and among the hubs, there is a score that tells how important their role as a connectors. So if you think about the social network, you can think about roles of that people play that generate, say, for example, content, and those that are sort of help this content propagate and connect people. So it's actually pretty cool stuff. Now, the only problem here compared to PageRank that unfortunately this type of algorithm does not scale too well, which means when you get to the sizes of the graphs of maybe thousands of nodes, the differentiating power of this algorithm diminishes, and it cannot distinguish very well between nodes, which means it started assigning very similar values of hubs and authorities to different nodes. But if your graph is relatively small, which means 1,000 nodes, and for a lot of networks, in social sciences, that's a pretty large size. Hubs authorities is very cool algorithm to look at. And again, with iGraph, you just call this hub score, authority score on your matrix, and it just on your graph, and it just gives it to you. So getting back to, pretty much done with the lecture, getting back to the picture we started with today. So this is a marriage network. There's the Florentines family marriage network, the one we saw in the very first slide. We can look at the different centrality metrics. And what happens, in fact, Medici family has the highest between the centrality score, if you calculate them. It has almost highest highest largest closeness centrality, and it has highest degree centrality. Now, there are other centralities we did not talk about, but here's Eigenvector centrality. It's also pretty high. And here's this PageRank centrality, which is we just discussed. And in fact, you can calculate PageRank centrality also for undirected graph, if you need to. It's also pretty high. So you can actually put forward a hypothesis that one of the reasons of Medici family, Medici house coming to power was with their strategic sort of marriages with other families in Florentine back then, and that positioned them as a central to pretty much all the discussions, all the decisions that has been made back then, and brought them into power. So, and our simple metrics can easily show you that in this graph, it's Medici who ruled that world, which is not very obvious just by looking at this picture, because they don't seem to be like very much in the center, but in fact they are. So that's pretty much it for today. Questions? Or everybody's asleep in the dark room. As always, there are references. You know, I encourage you guys to read them, or at least to quickly look through them. There are a lot of references here because there's a lot of sort of work done in sociology. And here is the last papers. These are work done in computer science. Oh, and here's a PageRank original paper. And you can actually, you know, see it, at least take a look at the original paper written by, you know, the founders of Google. It's probably the most famous paper out there by Brin and Page on PageRank. Okay. So if there's no questions, we're done for today, and Andrej will take care of the rest of the class on the seminar. Thank you.
Bye.